Well done, you made the right choice. This is my circuit. I've designed a circuit that senses temperature and humidity in a growing environment such as a greenhouse. And plants typically operate the best under a specific range of values for temperature and humidity. So to achieve that, I needed a circuit that incorporated hysteresis. The circuit design that I picked was a Schmidt trigger, which is essentially a comparator using positive feedback and open loop gain, which means that the op amp will hit its positive rail or negative rail, essentially turning on or off an LED. That LED in this example represents, for the temperature, either turning on a fan or opening flaps of a greenhouse to allow airflow, anything to cool the temperature down. And for the humidity, the LED represents a mister being turned on or off. So for my variable resistors, I essentially looked up the part, searched out the data sheet, and found the resistance values at my specific ranges. And I used those values to determine the subsequent values of R1, R2, and R3 for the positive feedback. If you'll notice in the bottom left of the screen, as temperature rises, the voltage at the inverting terminal falls. It's an inversely proportional relationship. And for the humistor, it's opposite. It's a proportional relationship. And the reason being is the thermistor and the humistor need to result in opposite actions. So as the temperature goes high, the LED is on. But as the humidity goes high, the LED needs to be off. So the way that I did this was simply by swapping the variable resistor with the 10K ohm resistor in the voltage divider. And that achieved what I needed to achieve. So moving on to hysteresis, in the middle, bottom middle, you see some formulas that represent the different thresholds for the voltage at the non-inverting terminal. As the op amp goes high, you essentially have a superposition of your reference voltage and the output voltage, which is the positive rail. And with an op amp connected to a 15 volt reference, that's roughly around 13.6 volts, 13.2, 13.6 volts for the output voltage. And when you're low, because the op amp is connected to ground, it's ideally 0 voltage for the output voltage. So you only have the VCC, the reference voltage. So that creates a difference that VN must overcome or undercome, go over or under. And for an op amp, when the voltage at the inverting terminal is greater than the voltage at the non-inverting terminal, you're going to hit your negative rail, and vice versa. So this was a quick run through of the circuit schematic that I have. And choose your next video wisely. Nice.